Welcome back. Now we'll be going into chapter 12.7. Yeah, 12.7 from the textbook, page 56. It's curvilinear motion, normal and tangential components. So the objective would be to determine the normal and tangential component of the velocity and acceleration of the particle traveling along a curved path. So we are still on the curved path. Remember the curved path earlier that we did? Yeah, we're still there. Yeah. Application. You see the car traveling on a clover leaf. Have you seen this clover leaf interchange? Malaysia has, yeah. Couple of places. One is Shah Alam itself. In Shah Alam, you can just use your Google map and look at Shah Alam interchange. There is a clover leaf. Yeah, so car traveling along the clover leaf interchange experience an acceleration due to the change in velocity as well as due to the change in the direction of the velocity. So when it's going in a curve, yeah, in a curve. So that's what they are trying to explain here. If the car's speed is increasing at a known rate as it travels along the curve, how can it be determined? How can determine the magnitude and direction of the total acceleration? So that's why we have to study this chapter. Another application is when, example, as a boy swings upward in a velocity, his motion can be analyzed by coordinate of n and t. Yeah, this is a swing, a boy on the swing. Yeah. So if you see, can you see the AN is actually moving to the circular path, which is locked in here, and AT is always tangential. I'll explain shortly. Yeah, and this is a roller coaster travels along the downhill, which following the path. The path is actually given. This is the roller coaster's path. So how do you use the path to actually determine the acceleration and the velocity? Not only at the bottom, but any point that is required by the question. Yeah. So now, moving on to the normal and tangential components itself. So if a particle, yeah, moves along a curvilinear path, yeah, example like this particle here, yeah, so this particle will have a tangential component and a normal component. Tangential and a normal component of velocity. Sorry, not a velocity, acceleration. Yeah, acceleration. So you have AN and you have AT. Okay, so let's move on. So where do you get this AN and AT from? Yeah, so the positive N and T directions are defined by the unit vectors AN and AT, tangential and normal. Yeah, normal is towards the center and tangential is towards the perpendicular distance. Yeah, the center curve of O always lies in the concave side of the curve. So you see this is the curve, right? It will be always in the concave side. Okay, it will be there. Yeah, and it's defined as the perpendicular distance and the radius of the curvature. So if you have a perfect circle, then this is the radius R. But if you have something which is not perfect, yeah, because this radius you see here is radius because it's perfect line. So always R. But in a curve path or a skiing path or whatever road, we always use rho. Because this radius is not the same. It's changing at all time. Yeah, it changes based on an equation. That's the reason why you call it rho. Yeah, so rho in a circle, in a perfect circle, is the R. Yeah, that's the difference. Yeah, okay. So we have the velocity component. Okay, so what we have here is V equals to V ut, or the V is ds dt. So the V is actually a tangential component. So remember what I told you about A, you have AN and AT, right? So dV dt actually contributes to AT, A tangential, not the AN, yeah? It contributes to the A tangential. So how do you get your dV dt? How do you get your V? You actually got it from ds dt. So how do you get your AT? You get it from dV dt. Okay, so remember that, yeah? Okay, now of course the combination of so what we have here, okay, remember the dot, V dot, yeah, V dot represents the change of the magnitude of the velocity and ut represents the change in the change of ut. This is just unit vector to show the direction. Yeah, okay. Now A, what is A? A is made of two components. One is the tangential component and another one is the normal component. Okay. So where do you get the normal component from? Yeah, the normal component is the one that is heading towards inward. It's heading towards inward. Can you see this UN? Okay, UN. towards the invert, the concave side. Remember? Okay. So what is this AN? AN is V square over R. Yeah, AN is V square over R. So in this case, they don't use R, they use rho. You know why? Because not all the time it will be a perfect square, right? Yeah, so that's why AN equals to V square over rho. Yeah, so the what you call the total acceleration is actually a combination of the tangential and the normal put together. Yeah, okay, you see that in the next slide. Can you see this? This vector, acceleration vector, AT UT. UT is just the unit vector to show its tangential axis, and A and UN. So what is AT? AT is your dvdt. Yeah, AT is dvdt. It comes from the tangential component. Okay, whereas the N normal comes from the V square over rho. So what is the V? That's the velocity. They will be given, most of the time is given in the question. Okay, so how do you find your magnitude? AT square plus AN square, inverse square root the whole thing. Yeah, so that is the magnitude. Okay, so we are going to go into solving the in textbook. I'm at page 12.7 chapter 12.7, page 56, 57. Yeah, 57 and 58. Yeah, so we're going to skip the three-dimensional motion part. Okay, this is the example. As usual, I'll skip the example in the lecture note. I will straight go to the example in the textbook itself, which is a bit more challenging. Okay, so let's look at this example in the textbook. Okay, let's look at this. When the skier reaches point A, so where's point A? Okay, right in the middle here, point A. Along the parabolic path, he has a speed of 6. So at that point A, the speed is 6 meters per second. Yeah, and increasing velocity, acceleration is actually increasing at 2 meters per second. Yeah, 2 meters per second. Determine the direction of his velocity and direction of the magnitude of his acceleration at this instant. So which instant? At point A. Yeah, so point A is about 5 meters, 5 meters in height. Yeah, in y-axis. And 10 meters in x-axis. So that is the coordinate. Okay, so what is the parabola that's given? Y equals to 1 over 20 x square. So what is dy dx? 1 over 10 x. And okay, so at, you see, because they're asking you at point A, right? So when at point A, what will the x coordinate is 10. Okay, what is the dy dx at point 10 meters? So you plug in the 10 into this x, yeah, because the coordinate is 10, right? So what do you get? 1. Okay, so keep this all aside. Okay, okay, so VA 6 meters per second, the coordinate is 45. How do you get this 45? Remember the dy dx is 1. Yeah, dy dx, you inverse tangent, you get 45. Yeah, dy dx inverse tangent of 1, you get 45 degrees. Okay, now let's solve for the rho, because this is the standard formula of rho. Yeah, this is the standard formula of rho. You can find it on your textbook. Textbook page 59. It's in the green box. Can you see right at the bottom? So that's the standard formula. It looks very complicated, but it's actually very easy. I'll just break it down here to make it easier for you to understand. So 1, no problem. Dy dx. What was the dy dx just now? You know, at coordinate 10, right? So coordinate 10, dy dx is 1. So you plug in 1 here. Dy dx square. Sorry. Dy dx. We are just getting the general one. Dy dx is 1 over 10. So 1 over 10 x. So you square it. So you have 1 over 10 x square. And all this you just have to follow. And then we have differentiated twice. Yeah. So 1 over 10 x, you differentiate again, you get 1 over 10. Right? So we need to find at coordinate x equals to 10. So plug in the values of 10 into all this x. So what do you get? 28.28. So the rho at point A is 28.28. So you just have to remember that. Okay, so now we are finding the acceleration. Acceleration you cannot forget. Yeah, it is 2 components for curvilinear, AN and AT. You cannot ignore either one. Yeah, so what is the AT? What is given for AT? Okay, let's look at that. We have 2. Where do you get the 2 from? Okay, remember the question? It's actually telling you that the acceleration is 2. That is the tangential acceleration. 2 ut. Ut is nothing. It's just to show unit vector which is in tangent direction. Okay. Next we have v square over rho. So what is the v? V value is given in the question, which is 6. So 6 square divided by rho. What is the rho at 10 meter? 28.28. Plug it in. So what do you get? You get 1.273. So this is just to show the direction. Ut and un is to show the direction. So what is the magnitude? 2.37. Square of 2, square of 1.273, you get 2.37. And then what is the angle? The angle will be tangent 2 over 1.273. So that's how you get your 57.5. Okay, so 57.5 degrees. So now, can you see this? This thing here is a bit complicated, yeah, because 57.5 is actually between ut and un. If you want to bring back, this 57.5 here, you need to show the calculation. So this is how it is, yeah. So you just pay attention. It's a bit tricky here, yeah. Okay, I'm going to play along with the axis now, so you pay attention. Okay, so if it's a flat axis, yeah, flat axis. So what do you have here? You have a flat axis, right? So that is why it is 45. Where did you get the 45 from? Here, the earlier one. So 45 plus 90. So first it's flat axis, 45 plus 90 plus with the 57.5 that you have calculated. Now we want to change the axis to this line, right? So this line. So what do? You minus with 180. So which means the angle in between here is actually 12.5 with the acceleration of 2.37 meter square. So this example is actually in on page 12.14. So you need to solve example 12.15 and 12.16 by yourself. Yeah, follow the study guide itself on what that you need to upload. So this is the end of this chapter, this sub chapter, sorry.